Okay, this is the replacement set of notes for 1A for Math 4. I had originally done these in front of a whiteboard, but people were telling me they can't see it and they can't hear me. So here we go. Here's the replacement. We start with what the goals are for today. One of the things that we'll be looking at is kind of a review for Math 3. We'll be looking at the key features of these graphs like domain, range, X and Y intercepts, increase, decrease, max, min, and behavior, all that good stuff for Math 3. We're going to review that. We're going to start with some definitions, which, some of this is going to be old school, but, hey, when y'all come into the classroom, I realize that each of you came from different backgrounds and different teachers, and so I can't assume that everybody is on the same playing field. So I'm kind of going back and hitting some basics before we move ahead. The domain is basically the set, helps if I engage my pen. All right, the set of all X values. And the range is a set of all Y values. And my cats are scrabbling. Okay, let's see if that gets them to settle down. Now, for example 1, we're looking at finding the domain and range. Write them both as inequalities and as interval notation. So first we'll start with the domain. Oops. And domain as an inequality. Now it starts here, 1, 2, 3, that's -4, 5, 6, 7, 8, that's +9 on that end. So X is going to be between -4 and 9. And when you think about it, those are dots on the end, which means that they are included in the answer, which means that's going to be less than or equal to on both sides. Now, to do that in interval notation, we would do this in this fashion with brackets on the end indicating that there is a closed dot on each end and not an open circle. Now, meanwhile, with the range, it goes from -5 up to +5. So we're going to say that from -5, and again, there is a clear point up there at the top. So that counts as part of the answer, and the range is going to involve Y's. So that's going to look like that. And then as far as the interval notation, it's going to look like that to that. And again, there are closed circles on both ends. So that's what the domain and range are going to look like for that graph. Very unique graph. All right, X-intercept is the coordinates where the graph crosses the x-axis. If I can get it spit out correctly. Crosses x-axis. Yes, I used to talk for a living. All right, and the y-intercept is going to be the same thing where it crosses the y-axis. Okay. Now, for example 2, it's sort of similar to the last graph. It's slightly different. And the x-intercepts and the y-intercept. All right, the x-intercepts are happening at -3 and at +3 and at +7, and the y-intercept is happening at 3. Now, I do want to say this, that for these intercepts like this, I would prefer you to use full ordered pairs, like that, and then 7 and 0. And then my y-intercept is going to be 0, 3. Now, for a while I kept getting it backwards. Does the number go on the left or the right? Where does the 0 go? And suddenly it occurred to me, the X-intercept, there's going to be a number for X, and it's going to go in the X's place. So for the X-intercept, the number always goes where X is, and the 0 goes the other way. And the Y-intercept does the exact same thing. It's going to, since the Y-intercept is 3, the 3 is going where the Y is in the ordered pair, and the 0 goes to the other place. So, all right. Now we're talking about relative minimum or local minimum, absolute minimum, relative max, and absolute max. Relative minimum is locally the lowest point. And absolute minimum would be absolutely the lowest point. And you're going to make a similar argument for the maximums, because your relative is going to be locally. Now, when I say locally, here's the picture that I want to go through your mind. It's kind of like you have the ability on your laptop with some of the clip and paste functions that you can draw a box around something and clip and paste it, copy it, and then paste it somewhere else. Well, imagine with the locally, if you were doing that in the area where there was a mountaintop on the graph, or maybe there was a valley down at the bottom of the graph. You are talking about a local maximum if it's a mountaintop, and a minimum if it's a valley. And so now, one question that has to be answered here is it possible to be both a absolute and a local max at the same time? Can it be an absolute and a local min at the same time? The answer is yes. I used to teach it the other way, and I discovered over this past summer that I was teaching it wrong. That if you have, let's say that you have a parabola that is doing that, and that is its highest point in the entire graph. Not only is that an absolute max, but it also counts as a relative max, because anytime that you have a mountaintop in your graph, that is at least going to be a local max. And if it's the highest place ever on the graph, then it counts also as an absolute. You get to call it both. Now, when we're looking at the other end, is there an absolute minimum here? No, because these arrows go on forever. There is no point that I can highlight, that I can draw a dot on it and say that's the lowest point ever, because those arrows keep going forever. So when we ask about the local min or the absolute min, our answer is the null set, that that 0 with a slash through it. Sometimes you will see me, if the arrows go on forever, I'll do positive infinity if they go up and negative infinity if they go down. But a lot of tests, I'm beginning to realize that they're just leaning toward the null set. If the arrows are going down like this red graph, then there is no such thing as an absolute minimum because the arrows go forever. All right, let's move on. Name the extrema. That is the fancy term right there for all four of what we just did. The absolute minimum, the absolute max, the relative min, the relative max. So let's see now. Let's say that, first of all, this point over here qualifies as both an absolute and a relative minimum. That is the point -4, -5. Is an absolute and a relative minimum. And we'll take the next point here, kind of moving left to right. That is -2, +5 is an absolute and a relative max. And the next point we run across is down here. This is a relative minimum, and so is this guy. Now, the thing that they don't mark here is that this guy right here qualifies as a relative max. We're going to catch all of these. Let's start with that was 5 and -4 is a relative min. And the next ordered pair is 7, 0. That is a relative max. And then the next ordered pair is 9, -2. And that is a relative min. So when we name something as an absolute minimum or an absolute maximum, it also gets the term relative as well. All right, increasing and decreasing. That would be the portion of a graph where the y value is, oh, wait a minute now. I'm thinking of positive and negative. I'm getting ahead of myself here. Is increasing. Don't have to change that. And portion of the graph where the y value is decreasing. Now, I will say this about increase, decrease, and positive and negative. You're going to have to play a certain game with this because we're all used to, if you're looking at where it's increasing and decreasing, you're used to paying attention to what y is doing. Y is the one that's going up and going down. That's the increase and the decrease part. But here's the trouble with this, is that as we are watching what y is doing, we're supposed to be writing what x is doing. I think I'm going to stop. Yeah. Well, no, I am going to finish this, and then I'm going to pause after this. So these shaded regions here, this is the same graph, actually, when you think about it. It's the same one we've been playing with all along. But the orange portions are where it's going up, y is increasing, and the blue portions are where y is going down. Now, what you will sometimes see me do as I'm walking through is that I will watch what's happening here, and I will mark. Now that is a solid dot, so we are stopping at 1, 2, 3, -4, and then this is -2 on the x-axis, and then over here is 5, and then over here is 7 and 9, and it goes the same here. Now, I'm going to leave off the brackets and the parentheses to begin with because I want to do this, and then we're going to go back and have a conversation about who gets the parentheses and who gets the brackets. First of all, let's do increasing. All right, so increasing, x goes from -4 to -2. Again, I'm leaving off the parentheses and brackets for right now. And then there's a union with another segment that goes from 5 to 7. Again, you are paying attention to what y is doing, but you are writing what x is doing. Now, -4, there is a solid dot down here. It's kind of cut off, but you can see it down here. That is a solid dot, which means that there is a definite starting point for this. But when we get up here to -2, something unique happens. It's kind of like you're on a roller coaster and you get up to the top and your stomach does that business. And, for just a brief moment, you're not going up and you're not going down. You're not doing either one. Well, when we reach the top of the roller coaster like that, it's not increasing and it's not decreasing. So that point where x is -2 does not count either way. So I'm going to have to do this because -2 is not a part of the solution. It's like there's an open circle there as far as increase and decrease is concerned. Now, the same thing is happening over here with 5 and 7. Down here at the bottom, when you're at the very bottom of the valley, you're not going up or down. So you can't count 5 as part of the increase. And the same thing happens up here at the top at 7. So you're doing all of that. Now, when we get to the decreasing part, decreasing goes from -2 to 5, and then it picks up again with 7 to 9. And at -2, of course, there's that top of the mountain, so we do a parenthesis. 5 represents the bottom of the mountain, so we do another parenthesis. 7 represents the top of the mountain, so we do another parenthesis. But 9 is a stopping place, and there's a solid dot right there, and it's not going up or down. So it counts as part of the solution. Now, I'm going to warn you about something here, because sometimes people like to look at problems like this and feel like they can develop a pattern of when I should do the brackets and when I should do the parentheses, and all of my answers are going to look just like this, and so I know where my brackets should go, and and it's like you're not paying attention to what the graph is actually doing, and that will end badly. You need to not fall into about the only thing that you can count on with brackets and parentheses like this is the fact that negative infinity and positive infinity never ever get a square bracket. They always get a parenthesis. That you can count on. You can also count on the negative infinity going on the left and the positive infinity going on the right. We like to do it on the number line from left to right, as it were, on the x-axis. So, all right, I'm going to pause there, and we're going to pick up the notes in the next video.